Dr. Barbour, we're going to continue on with the scheme as it is.
The focus of my group is really on technology and methodology development, and today I'll speak about our efforts to apply network descriptions to time series measures with the goal to extend the information content that can be accessed. In considering a network measure, particularly for the brain, typically explored as measures of temporal similarity, which for the resting state are made over a period of several minutes. While we consider similar measures, our focus instead has been to consider much shorter time periods, less than 1 second, with the goal to examine system kinetic and thermodynamic properties. So whereas some find the time-evolving properties of the brain interesting, imagine some people here, it's not the only tissue type that whose temporal dynamics are influenced by disease. Our focus is on breast cancer, and we look at the impact of resting state dynamics on the hemoglobin signal. In terms of the resting state, it reflects actions of aggregate actions of homeostatic mechanisms, which are often targets of disease and are easily performed, are well tolerated and suitable to all subjects. Stated differently, our hypothesis is that disease-related changes to the molecular interactome, such as the tumor phenotype, will impact the observable kinetic and thermodynamic properties. So how do we do this? Step one is we need to build an instrument. Developed was a high-density tomography system, shown over here, which allows for simultaneous bilateral measurements of breast, along with, if needed, concurrent viscoelastic measures. So in effect, what we just developed was a system that was intended to mimic a clinical breast exam. Okay. From this, we get wavelength-dependent measures, which we then compute a 3D image time series for each wavelength, and from that we can compute corresponding images associated for oxy, deoxy, total hemoglobin, hemoglobin oxygen saturation, and another component called tissue oxygen exchange. So we get 5 sets of image time series out of this. Okay. So given this information, the goal is then to translate this into a network format. So how do we do this? Well, given that, so we're looking at a resting state measure at any instant in time, some of the features are going to be above the temporal mean, some can be below the temporal mean. We can then, using an algebraic sign assignment, so those that are above or below the temporal mean, we just score that. And when you look at the combinations that you can get, there's 10 possible combinations across these 5 different components. This gives us 10 states. A description of that is shown here. So here I show a plot of oxygen saturation versus total hemoglobin. First, you get 4 quadrants out of this. If you add additional quadrants, or rather additional components such as oxy, deoxy, and so on, you can further segment this into 10 states. All right. So if you now consider a point in space and follow its trajectory over time, and do this for all different states, you can get a plot such as this, which is simply a cloud of points. Right? So we get this. So we do a measure over, say, a 10-minute time frame. I assign this network description, and then we can get this cloud of points. So if you compare that for tumor breast and normal breast, all right, you can see differences, but otherwise it's not very informative. So how do you take this information and distill it into something that actually is useful? That's the goal here. All right. So given that we can define these discrete points here, we have the opportunity to explore when we undergo a transition, which transition type. So it gives us 3 classes of information. We can get transition probability, and there's 100 different types of these. We can get measures of dwell time, both pre and post dwell time, and we can get measures of component amplitude. Given that we have 5 components, that's 5 for pre, 5 for post, and the difference between the two, we get 5 flux measures. So we get 18 sets of adjacency matrices out of this. So we start with a resting state measure made on a peripheral tissue, and we can derive very granular information that we were able to show is disease sensitive, and that this strategy can be applied not only to the breast or any other part of the body, it can be applied to any kind of time series measure. So for this community, I think would be of particular interest. I did this to be extended to EEG measures. Okay. So drawing your attention over here, these are just examples of the adjacency matrices that we can derive. So the way you read this is you have 10 different pre-transition states along the row, and that transitions into a fixed post-transition state. Along a column, it's one. You start with a pre-transition state, a single transition state, and they can undergo a transition to 10 different post-transition states. So then you get these 100 coefficients from here. And here, all I'm showing is sort of transition probability. The color scale reflects the amplitude. This is what we see for dwell time. Here it is for total hemoglobin oxygen saturation. The point is, if you look at a casual inspection, they're all different. Right? So there's a lot of differential information that can be acquired. If you look at the disease sensitivity, more than half of these pixels, these elements here are disease sensitive. We even showed that if you have, depending on whether it's estrogen positive or negative or HER2 positive negative, that also influences the patterning that you see. So a lot of information here. Now my talk is supposed to be on looking at structured behavior. When I look at this information, it looks like a Rorschach test. Right? So how do we distill structured information out of something as granular as this? All right, so the starting point is, so we understand we're studying a high-dimensional system. Typically what you want to do is look for codependencies. So we have 18 different sets of adjacency matrices. We can plot one against the other. And that, if you look through all the possible combinations of 153 pairings that you can get, we looked at every single one, right? And so if you consider the null hypothesis, transition probability, dwell time, and component amplitude, for an arbitrary system, all independent of each other. So if you plot one against the other, you expect to see a cloud of points. We did see that in some cases, but more often what we saw was evidence, what I show you here. So here is an example when we plot saturation, pre-transition against post-total hemoglobin, and what we see is these very smoothly varying functions. When we fit it to a functional form, it turned out to be, in many cases, hyperbolic. A hyperbolic function suggests a statural phenomena, which to us suggests enzyme-like activity. Non-invasive measure, we're looking for enzyme-like activity. All right, so this is what we see when we look saturation versus total. If we looked at other components, such as flux, we could even get more evidence of hyperbolic functions. So, in effect, what we're looking at is row and column information from these matrices. Is there any other information that you can get from these things? Well, actually, there is. You can look at the diagonal components, and that's shown here. By this, what I'm looking at is, so you have a transition from state 1 to state 2. That's one step. You go 2 to 3 and so on. So you have a set of information that speaks to a fixed offset. From there, you can go, so you can look at multiple of these fixed offsets here, and that's the plot is shown here. So actually, this plot here and this plot here are identical. We just...
There's no, there's no cursor on the...
No?
On the projection.
Okay, sorry.
And 2 minutes.
Oh, okay. So on the left-hand side here, what the heck, over here, left-hand side, doing both places. On the left-hand side, we have a figure, we see a set of points there. Upper right-hand side, we have another set. Those two data sets are identical, we just relabeled them. What we were able to derive from there was the fact that we can, in both cases, we can see evidence of hyperbolic behavior. So what this suggested to us is, all right, let's look to combine information. It's nice that we can see all this structured information. How about something as simple as a line-Rupert plot? So what we were able to do is we considered a three-dimensional vector from saturation, total, and dwell time. Let's plot it on the y-axis. On the x-axis, we show a measure of transition probability. From this, we're getting a fit of, or this is a group level finding, N of 18. Correlation coefficient 0.998. When we look at for N of 45, this is our healthy controls, correlation coefficient 0.995. Right? So this is, to me, fairly unmistakable evidence that we're able to appreciate enzyme-like behavior, almost certainly dealing with features of vascular pulsatility, and what we're also able to show that there's a disease sensitivity here, which suggests reactions of nitric oxide, which we know primarily affects the Vmax. Okay? So this is, right, so there's other things I talk about in terms of applying this to the deriving thermodynamic coefficients. I won't get into that. So in effect, so just to summarize, the point is that we've been able to appreciate that given a time series measure, resting state measure, any tissue type, and we don't care what the technology is either, we're able to derive these highly granular descriptions from which we can derive both kinetic coefficients as well as thermodynamic.
Thank you very much, Dr. Barbour.